Okay, yeah, so okay, but yeah, any other questions about the exam? Are you all okay with that? I'll post the solutions later. Okay, so what were we talking about last time was functions, right? So I'm going to talk about Fundamental Theorem of Calculus, but I'm going to go back to pre-calculus first, and then we already talked about it a little bit, and then I'll go back to calculus 1, and then we'll talk about Fundamental Theorem of Calculus. So what was a function? Definition of a function. Okay, what was it? Or maybe I didn't write it down so precisely, right? So just tell me what you remember from what we talked about. What do you guys remember? I know you just took an exam, but
I'd say a rule that takes the domain element and sends it to a unique ring.
yeah, so it's a rule. I'll call it a rule that takes an input. So if you want to be precise, you call this a domain element, and sends it to a unique output. And if you want to be fancy, you can call this a range element. So, but the important thing is the function is some kind of algorithm or rule. It does something. It takes an input. It does something to it. And this is important that it sends it to something unique, right? So, somebody tell me any function. Somebody just tell me.
X cubed.
X cubed. Okay, f of x equals x cubed. This is a function. What does it do? You tell me an input, 5. I take 5 and I cube it. So f of 5 is 5 cubed, which is 125. So 5 goes into the machine. Something happens to it. 125 comes out. And graphically, you can, this is a function we know. We can graph it. In terms of being a function, what this unique output means is something that you probably learned is this, it passes this vertical line test. And then we talked about other functions, right? So tell me a function that doesn't look like this. X squared, okay, that looks kind of similar. Actually, let's draw it though, because it's a little different in some sense, right? Because this function satisfies this horizontal line test, right? If I have an element here and I have an element here, they map to different numbers, right? But here, like, for example, -2 squared is the same as +2 squared. That's okay, it's still a function, right? -2 goes to a unique output, it goes to 4. +2 also goes to a unique output, it goes to 4, right? It's okay that they're the same number. That's something called one-to-one or injective. This function is not one-to-one or injective. What about a function that doesn't look like this? So what was the example that we talked about last class was like, we can have a sports team, right? We can have a table. This can be like the sports player. This can be like the, I don't know, rebounds per game or something, right? Right, I say player A gets 10 rebounds per game. Player B gets 2 rebounds per game. Player C gets, some number of rebounds per game, right? So the input now is a name, right? And the output is a number still, right? But the point is that there's some rule, there's some algorithm to find this, right? You tell me the input, I just look up his stats and his or her stats, and I tell you what the output is. There's a way to find the output. So, okay, good. So now let's talk about something different for a minute, and we'll see how it ties in. Integral from 0 to 2, x cubed dx. Okay, what do I do? How do I solve this? Evaluate this integral. What should I write? Somebody say something.
X to the 4
Okay,
over
good.
4.
Evaluated from 0 to 2, which is 2 to the 4th over 4 minus 0, which is 4, right? Okay, this is a number, right? I say evaluate a definite integral, you give me a number. Okay, now evaluate a very similar integral. Now what do I write? It's the same process, right? So I write x to the 4th over 4 from 0 to 3. And what I get is 3 to the 4th over 4 minus 0, which is some number, which I don't know. And now if I say, okay, right, do this integral now. What do I do? The same thing, right? I do x to the 4th over 4, and now I evaluate from 0 to 5, and I get 5 to the 4th over 4 minus 0. And if I tell you to do more of them, you can just do this, right? There's an algorithm that you're doing here, right? Okay, what is changing in each of these problems? The upper limit of integration, right? So I'm gonna do something that's a little different, is I'm gonna put a variable there, right? So let's do this. Integral from 0 to t of x cubed dx is equal to. Okay, and now what is my answer? You can kind of see a pattern, right? What do I do is, when I integrate this, I kind of just put whatever this upper limit of integration is, I get that value to the 4th over 4. So you can kind of guess, maybe this is this t to the 4th over 4? And in this case, we can just check it, right? So t is, just think of t as another number now, and then we'll assume it's a variable, right? So if I want you to do this, I just do this same algorithm. It's x to the 4th over 4 evaluated from 0 to t, which is t to the 4th over 4 minus 0. So what I've done is I've told you that this thing, integral 0 to t of x cubed dx, is equal to t to the 4th over 4. And you see, this is true no matter what value of t I put in, right? If I put in 0 here, I get 0. If I put in a negative number here, I get a positive number. If I put in a positive number here, I get another positive number. And you can think, okay, this, I could write this as a function, right? There's a function that depends, the variable here, right, is this t, right? So that's the dependent variable. So there's kind of two dependent variables going on, right? There's the dependent variable here, and there's some kind of integration going on here. So don't be concerned. The dependent variable here is t. And if you forget about the integral sign, this looks like a function that you've seen before, right? If I told you, tell me about this function, g of t equals t to the 4th over 4, that's not alarming to anybody, right? That's a very standard function. But if I told you, okay, this is my function, then maybe it's a little confusing at first, right? But what I'm saying is that it's not actually confusing. It's just another function. And now, why does it satisfy our function rule in general? So this doesn't have to be x cubed here. This could be any function, any integrand here. And what I'm saying is that if I have, let's say I have a continuous function. So let f, or maybe I'll do a different letter, h of t be a continuous function. Okay, maybe actually let me use another letter so that we're not confused, h of s. Then the integral from 0 to t of h of s ds is a function. Is a function of, I'll say dependent variable is t. So now, think about the functions we had before, right? X squared. What do? You take the input, you square it, that's the output, right? Say my function is sine x. What do? I take the input, I take sine of it, whatever that means, and then that's the output, right? Here, what I'm saying is, my rule that I'm doing, or my algorithm, is not as easy as these elementary functions that we had before, but my algorithm is, I take my input t, I take this function and I integrate it from 0 to t. That's, for any t that I pick, what I get is a definite integral that you can evaluate, hopefully. And a definite integral is a number, right? It evaluates to a number. So for any t I put here, I get a number out, some number. That's what the definition of a function is, right? For any input, I get some output. So this is a function. Okay, is anybody concerned about that, confused? It's okay if you are, it's very confusing. So just be careful about the different variables going on. Keep in mind that there's this variable going on, and there's this variable. And so one way to think about this is, for example, if h is a positive function, y equals h, then, or t, let's say, then g of t equals the area under the curve from 0 to t. So given a t here, I can calculate this area, whatever it is, and that's what my function is. So you can think of it in that way, that the rule is, I'm going to look at my function, I'm going to calculate this area under the curve. My input is how far do I go out. And so you can see kind of this could translate back into problems that we've already done, right? Like if this is a velocity function, then my function here is going to be sort of a change in position function somehow, or a position function. Okay, any questions? Are you guys okay with that? Okay, so this is a function. So what are we interested in? When I talk about functions, what are we interested in? Let's see. Functions. What do I want to say? What's the word I want? What is interesting about them? What things do I want to know? Properties. What properties do I want to know about a function? So now I want you to think back to calculus 1 instead of pre-calculus. Pre-calculus is what is a function. Calculus 1 is we have functions, right? And what are we interested in for those functions? What kinds of properties are we interested in? What was a question that was asked of you in calculus 1? What did you have to do? Yeah, okay, good. First, is the function differentiable? Okay, what else? Yeah, is the function continuous? What else? Good, increasing or decreasing? What else? Concavity. What else? There's more, right? Critical points, good. Okay, critical points, and this is related to extreme values, right? And there are some other things. But, okay, what about, for this one, is the function differentiable? There's a related question. What's that? I don't always ask you what is the, I don't ask you, is the function differentiable sometimes, right? I ask you what is the derivative, right? What is the derivative? Okay, so now, big link between calculus 1 and calculus 2 is I defined a function for you now here. you know, it depends what this integrand is, what the function is, right? But this is a function. So now I can ask all of these questions about this function, right? I can ask you, is it continuous? Is it differentiable? What is its derivative? If it's differentiable, is it increasing or decreasing? Concavity, critical points, inflection points, extreme values, things like that. So now you can kind of do, I mean, in Calculus 1, you learned all these techniques like, how do I find the derivative? How do I find if it's continuous? How do I find the extreme values, take the derivative and set it to 0, things like that. And you just did those problems for all these various functions, x squared, x cubed, sine, e to the x, things like that. And now what I'm saying is we can ask those same questions about this function. Okay, so let's ask some of those questions. Okay, so this might be a little bit of a, if you haven't taken calculus in a while, which I guess some of you said you haven't, this might be a little bit of a refresher, right? So if I want to ask, let me pick a specific function. So let g of t equal the integral from 0 to t e to the t squared dt. Be careful. E to the x squared dx. So the first function that I said, we were integrating x cubed, and I said we could just cover this up because my function was just t to the 4th over 4. Now, I don't know what the antiderivative of that is, right? So we can't write it in a simpler form. So let's just leave it. This is what our function is, right? Okay, so now you can ask these questions, right? Is g of t continuous? Who remembers what continuous means?
Differentiable everywhere?
No, not quite. So for a function to be differentiable, it has to be continuous first. Differentiable is sort of stronger than continuous, yeah.
You can graph it without picking pencil up.
Yeah, okay, you can graph it without picking your pencil up. That's sort of what it means. You can graph it without picking your pencil up. Anybody else? Yeah.
There's no breaks.
There's no breaks, yeah.
It's not undefined at any point.
It shouldn't be undefined at any point. Yeah, maybe we can. It's a little ambiguous if that's required for continuity. For us, maybe we should say it is. Okay, let's just recall a limit definition. So I'll say this. G of t is continuous if the limit as t approaches a of g of t is equal to g of t. Okay, so what does it mean? It means that if my function looks something like this, this is a. This point is g of a, right? It's a value. And what this means is that the limit as t approaches a, so as my independent variable approaches a, my function value is approaching this value. So basically what it says is exactly what you said, that you can draw without picking your pencil up, right? Because this point is here. As I approach a on the x-axis or the t-axis, my chalk needs to approach this point that it is. So that's sort of what it means. And in terms of showing this is continuous, maybe we'll do something a little less rigorous, like maybe we'll think about it in terms of an area, right? So yeah, let's do a heuristic, right? So what is this function e of x squared? Do you know what it looks like? What does e of x squared look like? Okay, somebody's doing this. It's an exponential function, right? It looks like this on this side. What does it look like on this side? Okay, it's not this. E of x looks like that. It is e of x squared, right? So it does that again, right? Yeah. It's an even function, actually, right? If I plug in a negative value, I get the same thing. So let's think about what does this represent? It's a positive function, right? So it represents the area under the curve, right? So the area under the curve, this is 0. If I plug in t here, then this area is equal to g of t. Good. And let's think what it means to be continuous is, as I'm going along my t-axis or my x-axis, I don't do any kind of jumps, right? And I don't do any kind of holes here. And if we think about, if I were to try to draw a plot of t versus the area under the curve, let's think, would it be sort of smooth, right? And the answer is sort of that it would be, right? So what does it mean for a function to have kind of a jump discontinuity like this? It means that right here, I was this value down here, say 1, and then all of a sudden my value jumped all the way to 2, let's say. So it means that at some point, my function made a big change in a small amount of time. Now here, if I'm looking at area under the curve, right, if I move some small amount of time forward, my area doesn't change by very much. So there's going to be no breaks like this. If I move a little bit, my area is just going to increase just a little bit. Okay. So let's say, yes. You can prove this in a later class, let's say. Well, we won't be more rigorous than that. Okay, so if a function's continuous, then you can ask, is it differentiable? Okay, 2. Is g differentiable? How, in Calculus 1, how do you show that a function is differentiable? Or what's a way to show that function is differentiable? No, not quite. So you need it to be continuous, but that doesn't guarantee that it's differentiable, right? So absolute value function is continuous, but the derivative doesn't make sense here. Like the tangent line doesn't have a lot of fine slip, right? How can I show something's differentiable? So one answer is that you can try to compute its derivative, right? If I can compute the derivative of a function, then it has to be differentiable, right? How do you compute the derivative of a function? You have some rules, right? But all the rules that you learn in calculus, right, are not going to apply to this function. This is not a polynomial. You can't use a power rule. It's not a trig function, so you can't use any of these sine and cosine things. It's not any of these functions that you learn how to take the derivative, so how can we take the derivative? Yeah?
Can't you do the limit?
Yeah, okay, so the only way that we could take the derivative maybe is to use the definition of the derivative, right? So let's use a definition of a derivative and see if it's differentiable. If the limit exists, then it's differentiable, right? So try to calculate. Limit as h goes to 0, g of, okay, let's say t, so g of t plus h minus g of t divided by h. That's what the definition is, right? If this limit exists, then it equals g prime of t. Okay, so let's try to calculate this limit. let's try to calculate this limit. So if I want to calculate this limit, I should simplify it in some way, right? When you were calculating limits in Calc 1, you try to do some simplification. The first way to simplify is let's use the definition of g, right? Let's plug it in. So this is the limit as h goes to 0. Okay, and now what is g? G of t is this integral, right? So it's the integral from 0 to t plus h. The independent variable, right, goes in the upper limit of integration here. Of e to the x squared dx minus the integral, so g of t is integral from 0 to t of e to the x squared dx, and you divide by h, right? Okay, what can I do to simplify that? Multiply by the conjugate. I think you don't want to do that. You'll be in trouble if you do that. It's a good thought, though. Yeah, when you do these limits, that's actually a pretty common thing to do, right?
Yeah.
But okay, I have two integrals though, right? And they have something similar. Let me give you a hint. I want to write the numerator as one integral. What is the one integral that I need to write? What is this? These difference of integrals? What are these two integrals? What are they equal to in terms of one integral? What's that?
From 0 to h.
From 0 to h, not quite, but it's something very close to that. So it's going to be from t to t plus h, right? The e to the x squared dx over h. Because what am I doing? Let's go back to our drawing. My function looks like this. This is y equals e of x squared. Looks something like this. This is t. This is t plus h. So the integral from 0 to t plus h is this whole area. The integral from 0 to t is this red area. So if I subtract them, what I'm left with is this blue area, right? If I subtract the white area from the red area from the white area, I'm left with the blue area. Just the integral from 0 to t, or from t to t plus h, right? Okay, good. And now, how can I calculate this? It's not clear, but if you have some ideas, you can say them. So let me draw a bigger picture. Okay, so this is going to be t. This is going to be t plus h. And I'm interested in somehow I'm interested in this area divided by h. Right, so I'm sort of interested, let's call this a sub h maybe. What I'm interested in is the limit as h goes to 0 of a sub h over h. Yeah. Okay, yeah, very good. So somehow there's a division by b minus a here. That's right. So you're dividing by h here. If you look down here, what is b minus a is t plus h minus t, which is h. So somehow that's exactly what's happening is this is equal to, somehow there's still a limit out here, so we'll talk about that in a minute. But what you get is this area, which is the integral from t to t plus h of e to the x squared dx. divided by, I'll call it, I'll write it as b minus a, but b minus a is h, right?
So isn't the average? Or?
Yeah, so that's exactly right. So this is a formula for average value, right? So this is what this is, this piece without the limit. All right, this is equal to the limit, so let's leave the limit there, but forget about it for a minute. This is the average value. The average value of what? It's the average value of this function, which was y equals e to the x squared. So it's the average value of e to the x squared over interval t to t plus h, right? And, okay, what's the average value of e to the x squared over this interval? And now this interval is shrinking down to 0, right? So it's my average value of this function, the average height, and now this is going to get squeezed down. So what is the average value, the limit of the average value? It's not 1. It depends on what t is, right? It has to depend on t, right? If I move t over, it'll be different. So what is it? What if this value was 20? Then what would the average value be? What's that?
20 divided by 8.
Okay, so when we divided by this average value, or when we divide by this h already goes into the formula for average value, right? So kind of the h is sort of gone, right? Except for it's the average value over this interval. The interval's sort of tending down towards this point. Yeah?
Well, isn't the derivative of e to the x squared would just be e to the x squared, though, right?
So the derivative of e to the x squared,
The integral of
e to the x squared is e to the x squared, and then the chain rule says take the derivative of this, right? So times 2x. So you can't take an antiderivative here to figure this out. Okay, let me say this. Okay, we've gotten to this point where we're just interested in the average value of this function over this interval, and the interval's tending down to 0, right? So here, let's say this is 20. Is my average value bigger than 20 or less than 20? It's bigger than 20. Maybe the average value is something, let's say, maybe it's somewhere in the middle, right? It's somewhere about there. Now, if I make this interval shorter, did my average value go down or up? It went down, but it's still bigger than 20, right? It's still a little bigger than 20. Maybe it's there. Now, if I make this interval even shorter, it's still bigger than 20, but it's smaller, right? The average value is sort of tending down. And if this interval is super, super short, what is it? What value is it close to? 20. Okay, so this limit is, in this case, it's 20. I use this number 20, but what is this value actually at t? E to the t squared, right? So this is e to the t squared. Okay, so, where does the work go? It goes this board to this board to that board, right? And what did we show is we showed that if g of x is this, g of t is this, then the final thing we were doing was we were evaluating this limit, right? So then g prime of t is equal to e to the t squared. Okay, so that's a nice formula. And what does it look like in this? It looks like the integrand here, right? So in the last minute, I'm just going to state the fundamental theorem of calculus. Well, part 2. Well, I'll discuss it more next time. So fundamental theorem of calculus part 2 says that e to the x squared is not a special function. It can be any function here. So if f of x is continuous, I'm going to use a new letter. F of s is continuous on an interval A is in the interval. So don't worry about that too much. Then if f of x equals integral from a to x of f of s ds, then f prime of x equals f of x. F is an antiderivative. So what I said was the fundamental theorem of calculus sort of says that the derivative and the integral are opposite, right? So here what this is saying is if I take the derivative of an integral, I get the function back, right? So f prime of x is d dx of this integral, right? So I take the derivative of an integral, I get the function back somehow. So we'll talk more about it next time. Yeah, I mean, I would say start your homework for the next one, but you can relax over the weekend if you want to, because we just took an exam.